Have you ever just looked at a complex metal part, like a window frame or maybe a heavy-duty structural beam, and wondered, how in the world do they make that? How does it go from being just a simple, solid block of metal to something so intricate? Well, the secret is surprisingly simple, and it all starts with one single piece of raw material. I mean, just look at these. You've got T-shapes, C-channels, even hollow squares. And every single one of them started its life as a plain, boring, cylindrical chunk of metal called a billet. So how do you get from point A to point B? What kind of industrial magic is this? Believe it or not, almost all of these manufacturing processes boil down to one fundamental concept. You either push the metal through a shaped opening or you pull it. Seriously, that's it. These two basic forces literally shape the world around us. All right, so let's start with the push method. This is a massively important industrial process, and it's called extrusion.
You know, the best way to think about extrusion is something you probably do every single morning, squeezing toothpaste out of a tube. You apply pressure, and the paste is forced out through that little shaped opening at the end. Well, in manufacturing, the toothpaste is a superheated chunk of metal, and the tube is a crazy high-pressure industrial chamber. Same idea, just way more intense.
The actual process here, what we call direct extrusion, is pretty straightforward. First, you load that metal billet into a container. Then, a giant piston or ram comes in and pushes on it with just incredible force. The metal has nowhere else to go, so it's forced to squeeze through a shaped opening, the die, and it comes out the other side as this long, continuous, perfectly shaped part. So if extrusion is all about pushing, what's its counterpart? Well, now we're going to look at the art of pulling, a process we call drawing. And this is really the key difference. With extrusion, you're using compressive force to push a big chunk of metal through a die from behind it. But with drawing, you're using tensile force to pull a rod or a wire that's already formed through a die from the front, usually to make it thinner. It really is that simple, push versus pull. So, the whole point of drawing is reduction. You're taking something that's already a certain size and making its diameter smaller and smaller. This is exactly how we get everything from the tiny copper wires inside our electronics to the strong steel cables used in construction, and even the strings for guitars and pianos. Now here's where it gets interesting. Whether you're pushing or pulling, engineers have to make another really critical decision that completely changes the final product. Do you add heat to the equation? I mean, it seems like a huge extra step, right? And it takes a ton of energy. So why on earth would you go through all the trouble of heating a massive piece of metal until it's literally glowing hot before you even start shaping it? Well, it all comes down to a classic engineering trade-off. If you use hot extrusion, heating the metal makes it soft, pliable, almost like putty. That means you need way less force to shape it, and you can create these incredibly complex, intricate designs. The catch? You lose a bit of precision. On the other hand, cold extrusion, done at room temperature, gives you much stronger parts, a better surface finish, and really tight dimensional control. But the force you need is just astronomical. Okay, here's a perfect example of why you'd use hot extrusion. These aluminum heat sinks for computers. They need all of those super thin, complex fins to get rid of heat efficiently. Trying to make this shape out of cold metal? Forget about it. But by heating the aluminum, it flows through that complex die with no problem. Now, on the flip side, take a look at this part for a spark plug. It starts as a simple little slug of metal, and then it's cold extruded into this really precise, high-strength component. For something like this, strength and exact dimensions are everything, which makes cold extrusion the only real choice. But let's be real, we're talking about forces that can reshape solid steel and temperatures that can make it glow like the sun. This is an extreme environment, and things don't always go perfectly. So, what kind of problems can actually pop up when you're pushing metal to its absolute limits? Well, you can get some really nasty hidden defects. A classic one is something called chevron cracking. You get these arrowhead-shaped fractures that form right in the center of the part because the internal stresses are so intense. And the really scary part is, you can't even see them from the outside.
And that's exactly why this stuff is so critical. As the experts point out, if you don't catch these internal defects with inspections, they can cause a complete, catastrophic failure of the part later on when it's in use. It's a huge reminder of why quality control is absolutely everything in this business.
Okay, so we've looked at the science, we've seen the risks. Now let's bring it all back and connect these massive industrial processes to the stuff that we see and use every single day. First, just take a second to appreciate the sheer scale we're talking about.
This isn't some small machine in a little workshop. This is a horizontal hydraulic press, an absolute beast that's capable of generating thousands of tons of force. It can squeeze solid metal like it's a piece of clay.
And because those forces are so immense, smart design is absolutely crucial. You'll notice the best extruded parts tend to follow a few simple rules. They're symmetrical, they avoid sharp corners where stress can build up, they have nice uniform wall thicknesses, and they don't have any sudden, crazy changes in shape. All of this helps the metal flow smoothly and gives you a much better, stronger part in the end.
So think about it. The next time you look at a window frame, or an aluminum ladder, or a simple copper pipe, or even the electrical wires running through your walls, now you know. You'll know it was formed by either the incredible compressive force of extrusion or the powerful tensile force of drawing.
So I'm going to leave you with a final thought. You now know the simple, really elegant secret behind how countless metal objects in our world are actually made. So do this for me. Take a look around the room you're in right now. How many things can you find that were almost certainly shaped by being either pushed or pulled? I bet you'll be surprised.